Hi there, Physics 131. This is the pre-class video for class 30, in which we're in chapter 10 on vibrational motion, section 10.3, dynamics of simple harmonic motion. Remember, kinematics is how things move, dynamics is why things move, and so this is about forces. So remember, Hooke's law is the force of the spring on a cart or something is negative k times x. So imagine that a cart here is on a spring which is attached to a fixed wall on the other end. At zero, there's zero force. That's the equilibrium position of the cart. If you stretch the spring, so the cart is at positive x, then you've got a restoring force. And so the acceleration is that force, k times x, divided by the mass. And so you got acceleration is equal to negative k over m times x. And remember, actually, we have an equation for x. Where is it? It was a times cosine of 2 pi capital T over t. And you can actually plug this in. Well, anyway, you can plug this in and solve out for what the period is in terms of the mass and spring constant of the spring. So I'll talk in class a little bit more about this, but basically capital T, the period, is equal to 2 pi times the square root of m over k. So the higher the mass, the longer the period, and also the higher the spring constant, the lower the period. And remember, the period is 1 over the frequency, or the frequency is 1 over the period. So there's also a corresponding equation for the frequency of a cart vibrating on a spring. The frequency goes up as the spring constant goes up. The frequency goes down as the mass goes up. So, okay. To talk some examples there about a vibrating chair going up and down. And now that forces are done, she goes back to, this is section 10.4, energy of vibrational systems. So there are two kinds of energy. There's the kinetic and the potential. And so the kinetic energy is just 1/2 mv squared. That will be maximum when the object is passing through its equilibrium position. And the elastic potential energy is the energy stored in the spring. And that's maximum when the string is maximally stretched or maximally compressed. And so it turns out that it's 1/2 Ka squared is the maximum elastic potential energy, and then 1/2 mv max squared is the maximum kinetic energy. And since one is zero, one form of energy is zero when the other form of energy is at its maximum, then the total energy is just one or the other. You can either use 1/2 Ka squared or 1/2 mv max squared. Those are equal to each other, and they're equal to the total mass of the system. But in between the maximum of these two, it's 1/2 mv squared plus 1/2 kx squared. So as x changes, v changes. But you can rearrange that, and you can actually solve for the maximum speed of simple harmonic motion. It's square root of k over m times the amplitude. So that's a handy little equation right there. And this chapter ends with a little example about a body mass measurement device, BMMD chair, which they have on space stations, which measures the mass of an astronaut. When you have a known spring constant, then you can measure the frequency of vibrations and get the mass. And so far, this has all been about masses attached to springs, but there's many other kinds of systems that exhibit vibrational motion that can be modeled with this cosine that are not masses on springs. And so one of them is called the pendulum, simple pendulum. And basically all that is just a mass hanging from a string. So there's no springs involved here. It's just something that we've sort of done this a little bit before. It's actually circular motion. But if you just release the object not far from its bottom, then what you can think of is that if you have a mass or something that's hanging from a string, if you displace it a little bit away from its equilibrium, it wants to go back to the equilibrium. So that's a little bit like a restoring force. And that's exactly what they show here. If it's pulled to the right, then it wants to swing back towards the left. and if it's pulled to the left, it wants to swing back towards the right. So you have to work it out. You have to do a small angle approximation to really make this work. But eventually what we do is you get, you say x is equal to L times theta. That's the arc length equation we had before, where theta is measured in radians. And then there's a force, which is, I guess there's an approximation somewhere where the force is approximately equal to negative mg over L and times x. And so what that does is it gives you a period of oscillation, which is 2 pi times the square root of L over g, where g is that 9.8 meters per second squared, and L is the length of the pendulum. So we'll go through this a bit in class. You can model someone's leg as a simple pendulum and try to get the natural walking frequency. It turns out to be about 1 over 1.4 seconds. And so this sort of gives a natural walking speed. It also explains why if you have a shorter leg, your walking frequency is higher than if you have a longer leg. So little dogs, you'll see their legs will have a high frequency. So that's it for today's reading, and I'll see you next time. Bye for now.